Hello everyone, my name is Maria Fernanda Lopez Villarreal, and I'm a student of nanotechnology engineering. Today I will be presenting my project titled Microplastics Removal using Nanocellulose Derived from Sargassum Biomass. To start, microplastics are a growing environmental concern worldwide due to their widespread contamination and harmful impact on ecosystems and public health. The scientific community is actively seeking new and effective methods to reduce this pollution. Mexico is a significant contributor to global plastic consumption and pollution, so this project aims to develop a system for removing microplastics using foams derived from biomass of sargassum, an invasive algae affecting the coasts of Mexican Caribbean. This approach addresses two major environmental challenges faced in our country nowadays. So, first of all, we got the experimental phase, and it begins with extraction and isolation of nanocellulose from sargassum. This involved depolymerization and bleaching processes to obtain the purified nanocellulose. Additionally, we synthesized a dibutyric solvent using oxalic acid and choline chloride, which was used to functionalize part of the nanocellulose and compare its properties with the unmodified form. Next, we perform several characterizations to analyze the chemical composition and functional properties of the final materials. In the first picture of figure number 2, we observe the IR spectra at different stages of the nanocellulose isolation process, as well as in the next picture, we got the kinetics, the reaction kinetics with the deep eutectic solvent. The spectra both clearly show the characteristic cellulose signals such as carbon and oxygen bonds and the main functional groups. We also detect signals from magnesium and calcium ions, which likely originate from marine impurities remaining in the sargassum. Interestingly, those ions contribute to improved properties once the nanocellulose is functionalized with solvent. The figure below, presents the X-ray diffraction patterns of the pre-treated sargassum powder, the isolated nanocellulose, and finally the functionalized cellulose. The diffraction peaks correspond to crystalline planes of cellulose type 1, confirming a mixture of alpha and beta phases. Peaks at 14, 16, and 22 degrees indicate specific planes related to these cellulose phases. Moreover, in the later stages, we identified compounds such as calcium oxalate and some magnesium ions. Their formation during this functionalization positively influenced the mechanical properties of the material, as shown by improved mechanical tests. And speaking of mechanical properties, we also test the nanocellulose foams to evaluate their resistance. The results reveal that the foam functionalized with the dibutyric solvent at 2% concentration exhibit the best mechanical behavior. So this balance likely comes from an optimal combination of increased crystallinity and the right amount of functionalizing agents. The foam at 2% shows a Young modulus of 48.05 megapascals, indicating a greater stiffness and mechanical strength compared to the other samples. And finally, we got the microscopic images of the foams reveal nanometric fibers, so forming a porous network with a reduced pore size. This structure is ideal for efficiently trapping small contaminants like micro and nanoplastics by minimizing free spaces and preventing their passage. We also conduct swelling tests to evaluate the foam's capacity to absorb water, which relates directly to their ability to capture microplastics. The foams with 2% nanocellulose dispersions, both functionalized and non-functionalized, demonstrate higher swelling capacities compared to other samples, which collapsed quickly, and after 10 minutes, the non-functionalized foams swelling decreased, showing loss of stability, while the functionalized one continued swelling until around 15 minutes, reaching a maximum capacity of 58.6 grams of water per gram of nanocellulose. Environmental conditions like pH and temperature were also tested. Optimal swelling occurred at a pH of 5.5 and room temperature around 25 degrees, confirming that these conditions are favorable for the material's microplastics removal performance in water. Finally, we developed kinetic models to describe the microplastic removal process. The swelling capacity and removal efficiency were significant and correlated using the Weber-Morris intraparticular diffusion model. We also identified 3 distinct phases in the process. We got the rapid surface diffusion. The second one is the diffusion inside pores, and the equilibrium stage. These models help us understand the mechanisms behind microplastics absorption and will guide future optimization of the systems. In conclusion, the nanocellulose extract from Sargassum shows great potential as a sustainable material for plastic contaminant removal. The bleaching and functionalization process yield nanocellulose with enhanced structural properties. The FTIR analysis confirmed presence of cellulose functional groups and ionic interactions with magnesium and calcium oxalates, while XRD showed an increase of crystallinity up to 70%, indicating effective purifications. Absorption studies demonstrate multi-layer deposition of microplastics on the foam's porous structure. The kinetic models confirm a 3-stage absorption mechanism, reinforcing the material's suitability for water treatment applications aimed at mitigating microplastics pollution. Before I finish, I want to sincerely thank Dr. Miriam Esteves for her invaluable guidance and supervision, the Applied Biomaterials Laboratory for providing resources and space, and finally Cefatonam for their institutional support that made this research possible. Thank you very much for your attention.